Hello guys, so today we're going to be doing the third week's lecture, which is intermolecular forces, solutions, colloids, chemical equilibrium. This week, I'm going to be honest with you guys, this week's content for MedChem is crazy. This is going to be a big video. I don't know how long. 1 hour for sure, 2 hours maybe, 1.5 hour high likely, a high possibility. Okay, so let's get started. I don't want to waste the time, but I'm being honest. It's a big, fat lecture with a lot of concepts. So let's get right into it. First, we're gonna look at intramolecular and intermolecular forces. Okay, so I have the whole slide ready over here. Let's start with intramolecular forces, which is the forces which form a molecule. A molecule is made of one or two atoms. Two or more atoms. I'm sorry, two or more atoms. So the forces which combine these two or more atoms are called intramolecular forces. Okay, let's get into it. There are three intermolecular forces: ionic bonds, covalent bonds, and metallic bonds. Let's look at ionic bonds. They take place between metals and non-metals. This is very important because this is how you identify the bonds. Between metals and non-metals, we have an ionic bond. Over here, I have an example for you, and I'm going to show you how an ionic bond works. So, over here, we can see this NaCl. We have a metal and a non-metal right here. So, we can see in the valence shell of chlorine, we have one less electron. If chlorine gets this one electron over here, it completes 8 electrons in its final shell, hence completing the octet rule. Later on in this, I'm going to explain what the octet rule is in depth, but for now, just understand this. And over here in the sodium atom, we can see the valence shell has one electron. And if we remove this electron, the shell before it is complete, and this shell's octet rule is complete. So this wants to gain one electron, and this wants to lose one electron. And that's exactly what happens. This electron goes from here to here and joins here. Okay? Joins this gang. Now it's in the chlorine gang. So now what happens? Let me do this. I'm gonna cut this off here, indicating that there's no electron here anymore. And now there's one electron here. Okay? So now what happens is the shells over here, it's complete. This has completed its octet rule. This has completed its octet rule. They both are happy. Now what happens is, since this has more electrons than this has a slightly negative charge, and since this has less electrons compared to this has a positive charge. Okay, and this is how an ionic bond works. We know that opposites attract, so hence these attract each other, forming a bond. Okay, that's one of the reasons. Another reason we can say is because chlorine's electronegativity, that is later on I'm going to explain again, but electronegativity is the inherent property to attract electrons. Okay, and chlorine has more of that. So what happens is it attracts the electrons of sodium as well. Not completely, doesn't bring all of them here, but just the cloud in which the electrons exist is much bigger for chlorine, as you can see. This gives it a negative charge and this gives it positive, and hence they attract each other. That's how an ionic bond works. Covalent bonds. In covalent bonds, transfer of electrons does not take place, but instead what happens is they share electrons. So let's look at this. We have covalent bonds here, and these happen between non-metals only. Very important points here. You can take screenshots of this whole slide later on, and then you can remember. So let's take this. molecule, for example, F2. Over here we can see one electron belong to one of this and then another electron belong to one of this. Now they understood that if they share one of these both of these electrons, for this shell, let's neglect this part, okay? Let's neglect this part and let's just look at this. We can see that the octet rule is complete. But now when we look at this, the octet rule is also complete. But over here, what's happening is they create sort of this new orbital in which they are sharing these electrons. Okay? And because of this, the fact that they are sharing electrons, they form a bond, and that is the covalent bond. Now, there are two types of covalent bonds. There's polar covalent bonds and there's non-polar covalent bonds. Now, if we were to take some other molecule, like let's say we take HCl, okay? They have a covalent bond as well in between. But since chlorine has a higher electronegativity, it attracts more of the electrons from hydrogen over here. Hence, making the electron cloud around it way larger than hydrogen. So electron cloud is basically where electrons can exist. Okay? So this gives it a negative charge and this gives it a positive charge. Okay? But this is not the reason that they are attracted to each other. The main reason that they're attracted to each other is because of the covalent bond. But what happens is, because of the difference in electronegativity, there is a slight negative and a slight positive charge. This makes the whole the molecule of HCl polar. Okay? Again, in ionic bonds, this difference in electronegativity, or this difference in the number of electrons, creates a positive and negative, and this is the main reason that they attract each other. Okay? But in covalent bonds, the fact that they become positive and negative is just a side effect. That's not the main reason that they're attracting each other. The main reason that they are bonded together is because of the fact that they are sharing electrons. Okay? But we have also a class called non-polar covalent bonds, and that is exactly F2. Over here, the electronegativities are equal. So they both are attracting the electrons from both the atoms the same amount. So their electron clouds look very similar to each other. Hence, this is a non-polar covalent bond. There's no slightly negative, slightly positive charges, okay? And this is the non-polar covalent bond, okay? Again, ionic bonds are formed due to the reason that there is a positive and a negative charge, but in covalent bonds, that's not the deal. The main reason that they're bonded together in covalent bonds is because they're sharing electrons. Moving on, we have metallic bonds. Metallic bonds are their whole different league. We don't really talk about metallic bonds a lot, but they are there, so we need to talk about it. Metallic bonds happens between metals, okay? So you can see over here, what happens is when metal atoms are stacked together, okay, the electrons of the metals get delocalized, meaning they're not conformed to a boundary anymore. They're just floating everywhere. So the electrons of this atom could be floating anywhere here, and same goes for this and this. So basically what happens over here is electrons are everywhere in metallic bonds, okay? And because of electrons floating around and the presence of the nucleus, which we know is positive, there is electrostatic forces. And by electrostatic forces, I mean positive and negative. They attract each other. That's what happens. There are some properties of metallic bonds which we don't really need to know, but I'm just giving information here. Delocalized electrons, they're arranged in a regular pattern, okay, and then they conduct electricity because of this fact. Because of the fact that electrons are floating everywhere, we can conduct electricity with metals. The more you know. And it has a high melting and boiling point. High melting and boiling point because of the fact that there is so much electrostatic force all around. Since electrons are everywhere, they're getting attracted to the nucleuses of other atoms, but they're all the same basically. When I'm talking about iron metal, and a sheet of iron metal. All the atoms in that sheet are iron. So the electrons floating around in that help conduct electricity, and the attraction caused by the electrons in the nucleus, okay, that is the reason that it's so strong, and that is what we call a metallic bond. Okay, most important ones are ionic and covalent. Let's remember those. Okay, moving on, let's go to over here. This table, I think Mateen explained it in the last lecture, and I trust him to probably explained it really, really well. So electronegativity increases from left to right. Remember this. Electronegativity increases from left to right, and electronegativity is the inherent property of an atom to attract electrons. Okay. So look at this, and I'm gonna come back to it now. Let's talk about intermolecular forces. Okay. Now, intermolecular forces, I confuse this myself, so I don't want you guys to confuse it. HCl, for example, the bond holding H and Cl together is called intramolecular forces. But the bond holding HCl and HCl together, that is called intermolecular force. Intermolecular force, I'm so sorry. Intermolecular forces. So basically these forces here, these are called intermolecular forces. There are three subtypes, okay? Three types, and that starts from London dispersion forces, dipole-dipole interactions, and hydrogen bonds. Let's talk about, well, I'm going to explain them individually, all of them. I'm going to explain the concepts. London dispersion forces. They happen between non-polar molecules. And let me tell this, London dispersion forces are in every single molecule on the planet. Every single molecule. Every single molecule has London dispersion forces. And when I explain to you what London dispersion forces are, you'll understand why they exist everywhere. Dipole-dipole exists only between polar molecules, okay? Dipole-dipole, it makes sense. Polar only because polar molecules are the ones which contain dipoles, and dipole-dipole interaction suggests that the interaction only takes place between dipole-dipole. You get what I'm trying to say. Examples, I've given examples here. HClSO2. For non-polar, I've given examples here. And defining polar. I'm going to define polar for you again, okay? And hydrogen bonds. I'm going to explain hydrogen bonds in the next slide. Now let's explain what polar is. Polar and non-polar. Of course, we know polar is charges, has a plus and a minus, okay? But how do you just look at a molecule and understand if it's polar or non-polar? This is a trick I'm going to give you, okay? The lectures didn't tell us this. I'm the best, okay? Let me explain to you. There are 2 points, okay, to identify a polar molecule. They are no lone pairs. The central atom has no lone pairs, and the atoms surrounding the central atom are the same. Okay, so for example, let's say no, oh shit, I'm so sorry. What I just said, that the central atom has no lone pairs, and then the atoms around it are the same, that is for non-polar. I'm so sorry. I seem so messy, but I'm so sorry. Okay, that is non-polar. Let's explain that with an example. Let's take CH4. Okay, CH4. Okay, you can see over here that the central atom has no lone pairs, and the atoms surrounding it are all the same. Okay, hence we can definitively say that this is a non-polar molecule. Okay, but then how do you find what a polar molecule is? If it's not non-polar, it's polar. Simple. Okay, I'm going to keep repeating these points again and again throughout the whole lecture so that it gets stuck in your brain. Okay, let's start. London dispersion forces, or as Mr. Tibor says it, London dispersion forces. So in London dispersion forces, what happens? Let's take a normal atom, any atom, and I've drawn nucleus here, okay? And let's consider that it has one shell only. I'm going to draw a shell here. Yes. Let's fill it up with electrons. This is a very shit feature, but sometimes it's really nice as well. Now, how I have distributed the electrons is an ideal way. I would ideally want them to be spaced apart like that, okay, equally in equal distances. Now, when an atom is structured like this, where the electrons are spaced equally, okay, it results in a neutral atom, okay. But real life, it's not always like this, okay. Real life isn't perfect. So when when electrons are revolving around the nucleus, there may become some points where the electrons are all bunched up in one side. Maybe, I'm just saying that could happen. Maybe one electrons here, okay. So what this does is it divides this atom in half. Not really, but in a way. And that this part gets a negative charge and this part gets a positive charge. And that creates a dipole. Okay? But this is very temporary. This is like it keeps happening. Okay? Electrons are revolving around the nucleus. At some point, maybe there is more electrons on this side, maybe one less this side. Boom, dipole. But then they start revolving again, and you don't know what happens next. Maybe they're again equidistant now, and then after some time, boom, this side has more, this side has less. Boom, dipole again, interaction. This force happens. Okay. Now let's consider this. This happens. This is a negative side. Oh shit! Wait. This is negative, and this is positive, because this side has more electrons. Now it has a temporary dipole. This is what This is what we call a temporary dipole. That's so Indian. Temporary dipole. Okay. Now let's consider this. This is not London dispersion forces. Let's consider another atom with this, which is the same. I'm gonna just copy this, and I'm gonna paste it here. Paste. Okay. And ideally, I do not want these balls here. Because of this, because of the reason that I'm taking this much time, can this shit work? Okay. Now let's consider that this had equally spaced apart electrons. Due to this temporary dipole of this, what happens is, this is negative, right? So this repels the electron to this side. Okay. So now the condition over here as well is like this. Okay. And now this has a temporary charge. This is negative and this is positive. And now this side is negative. We know that. And guess what happens? They attract each other. Okay. But of course, this is temporary. And this dipole that is induced over here is called induced dipole. Okay. That's London dispersion forces. That's how they work. An atom, electrons revolving around the nucleus. At one point, what happens? This side has more electrons than this side. So then there's a charge difference. There's a dipole formed. Because of this dipole, the atom next to it has an induced dipole, and because of that, they're attracted to each other. This is on and off thing. Okay, this is an on and off thing, keeps happening, and this is present everywhere. Because think about it, all atoms have electrons which revolve around it. So this must happen everywhere, and it does happen everywhere. So that is London dispersion forces. Next, octet rule I was explaining to you again. Simple. I'm just gonna do this quick. Okay. Octet rule just says just explain to us how many electrons can be filled in a shell. Let's consider this the number of shells. The first shell is N1, the second shell is N2, and the third shell is N3, and then we can keep going on. The fourth shell is N4, 5, like that, okay? The rule of how many electrons can be fit in a shell is 2n square. That's the formula of how many electrons can be fit in one shell. Let's take that. Let's consider that for the first level. First level, it would be 2n square, which would be 2 into 1 square, which is 2. And that's exactly correct. 2 electrons is the minimum number of electrons that should be present in the first state. Then the second one. Second, we come on 2n square would be 2 into 2 square, which will be 2 into 4, which is 8. And yes, 8. 8 electrons are the number of electrons that should be present for stability. Okay? And then the shells after this, they keep increasing, of course. 2n square keeps increasing, and the number of electrons keeps increasing. But from the second shell onwards, all the shells above it should contain a minimum of 8 electrons. Not the first shell, the second and above. The minimum number of electrons that should be present in their shells is 8. And that's where we get the octet rule from. And if the electron shell, outermost shell, valence shell has 8 electrons, it's a stable electron. It's a stable atom. It means it has completed its octet rule. Okay? That's that. I'm not going to go any more into it. Okay? Let's talk about dipole interactions. Dipole interactions, very simple. They happen between polar covalent bonds. Okay? Now let's consider HCl. Polar covalent bond. Let's explain this again. The whole thing I'm going to explain it again. We see chlorine has 1 electron and it needs 1 more electron to complete its octet. Okay? Because this is the second shell has 8 already and it's complete. And after this, it's supposed to have how many? 3 square, that is 2 into 9, that is 18. Supposed to have 18, but that's the maximum number of electrons that it can have. Minimum, it should have 8. And 8, over here, just 1 more electron. Guess who has another electron? Hydrogen. And hydrogen can just share this electron with this. And then what happens? When it shares this electron with this, hydrogen completes its 2 electron state. That's what it needs for the first level, right? And chlorine completes its octet. Finished. So this is a covalent bond. They share electrons. But where does the polarity come from? It's so obvious, guys. Look at it. This guy has so many electrons. So when they share this bond, the fact that it has so many electrons makes it negative, and this side is positive. Easy. That's how polar covalent bonds is formed. Okay. And this happens now. Okay. Now this has I'm gonna just write it down. This has a plus charge, minus charge. Now let's take the same thing again because we're talking about intermolecular. We're not talking about intra. Okay, this is intra what I just explained. Polar covalent bonds. That's intramolecular forces. We're talking about inter here. So let's just do that. Copy this, paste this, and boom. You see, this thing undergoes this molecule undergoes the same thing. Okay, so this gets positive and this gets negative as well. But guess who else has a negative and positive charge? These atoms on the side. These atoms. See, positive, negative, they attract. And when you put trillions and millions of HCl molecules together, this is how they interact. Through dipole interactions. Understood? That's dipole. Hydrogen bonds. Okay. Very simple. I'm going to give you a brief. If you don't want to listen to this, you want to skip this, listen to this. Hydrogen bonds are formed between H and NOF. NOF. Okay, NOF. Nitrogen, oxygen, fluorine. If hydrogen forms a bond with any of these three, it's a hydrogen bond. Finish. But if you want to, let's listen to this. Let's understand this a bit more detail. Let's look at ethanol. Jar of ethanol. Let's zoom in. Let's say we zoom in, okay? A million times. Where we can see the molecules now, like that. Okay? You can see the molecules here. This is how they're scattered. Now, an important point. Okay? Now, you can see over here. What happens? Let's look at this. Okay, H over here, this bond over here is not neutral. Oxygen being more electronegative. Let's look at the electronegative chart again. Oxygen being more electronegative than hydrogen. Okay, what happens? Being more electronegative than hydrogen attracts more electrons here. So what happens is the cloud looks kind of like this. You see how the electron cloud for hydrogen is a bit small, but for this is a bit big. So this gets a slightly negative charge and this gets a slightly positive charge. Okay, and this happens for all of these molecules. And because this has a slightly positive and this has slightly negative, positive, negative, positive, negative, positive, negative, they attract each other. And this is how they form bonds. Understand? But does that mean that this H and this is a hydrogen bond? Does that mean that? No. Let me explain why this isn't a hydrogen bond. First of all, H is not attached to O or N or F. It's attached to a C. We don't care about C. Okay? So this is not a hydrogen bond. Okay, fine. Understand that. Now, can this hydrogen attached to the C make a bond like that with O? Will that be hydrogen bond? No. Okay? Hydrogen bonds will only be formed with OH, NH, FH. What I mean by this? Let me see. Let me show you over here. Let me make this a little fat. OH, NH, FH. Okay? When we have this condition, only then they will attract another OH or another NH or another FH. Same goes here. Okay? Same goes here as well. Okay? Just hydrogen alone cannot form hydrogen bonds. Hydrogen attached to an oxygen or a nitrogen or a fluorine can form hydrogen bonds. Understand? Why is this? Simple logic. I'm just going to explain because the electronegative, they have this positive and negative charges. That's the reason. Okay? These are hydrogen bonds. Just remember simply OH, NH, FH forming bonds with N, O or F. Boom. Done. Predicting the presence of a dipole moment, very simple, guys. If you know the periodic, obviously you won't know the periodic table, but if you have the periodic table, you know electronegativity increases from left to right. So if you see, like, suppose I'm just looking at this, I know that, see, as I said, polar molecules. Remember when I said in the start, to identify a polar molecule, we know that the central atoms do not have a lone pair, and all of the things, atoms around it should be the same. That will make it a non-polar. But over here you can see one of them is different. That makes it polar. Very simple, the way I told you, recognize. Okay, see, it's not polar, it's polar. It's polar. But if instead of Cl there was H over here as well, then it would be non-polar. Okay, I already talked about London dipole hydrogen, so we don't need to talk about that anymore. Identifying intermolecular. Let's identify the intermolecular forces. Identify the likely. HCl. We see an H. Okay, we see an H. Does that mean it's hydrogen? No, definitely not. We need to see if there is an O, if there is an N, or if there is an F. We don't see any of that here. Okay, simply we can say that it is a polar covalent bond. Okay, but then they're asking us to identify the intermolecular forces. What I just said was the intra. Okay, intermolecular forces. Since this has a dipole, which is because it has a polar covalent bond, this will have a dipole. This plus and this minus. So these the intermolecular forces this will use is dipole. Okay, this not polar. Okay, covalent, not polar and covalent. London dispersion forces. Not polar, covalent, London dispersion forces. Polar and covalent, dipole-dipole interaction. Over here, what do we see? We see an N, we see an H, NH. So hydrogen forces, none. Kr, I mean, we can say that it has London dispersion. London dispersion. Because everything in this world has London dispersion. And I was right. Comparing the boiling point. Oh, sleepy as shit, man. Okay, but CH4, CCl4. Compare the boiling points. Okay, we just need to see which has a stronger bond. Let me explain this very simple concept. C, wait, chill out, what happened? C, H, okay, but H has only one electron, okay? So C, one electron, one electron, one electron. Let's take it like that, okay? It's not like this, but let's take it like that. So when the electrons are less, the possibility of a stronger dipole is less. What do I mean by this? Let's take this side. One electron only here and one electron here. Let's say I put two electrons here, okay? That does give this a negative charge, this gives this a positive charge, but it's weak. Compare this to maybe, okay, that is definitely stronger because this has a large negative charge and that will attract positive way more, right? So for this to happen, we need more electrons, right? So more electrons equals more polarizability. Right here, the word right here, polarizability. More electrons, more polarizability. Higher the polarizability, more stronger the bond. Now we know Cl has more electrons than H, so this will be more polarizable, hence being stronger. That means Cl, carbon tetrachloride, has higher boiling point. Simple. Comparing, this is where I don't this very random topic just fit in. Boiling point, I've written over here. Where did it go? Boiling point inversely directly proportional to molar mass, inversely proportional to branching. Branching means if there is more branching, less boiling point. We don't want branching, we don't like branching. We want stuff to be in a straight line. So the same thing over here. Since this is branched, this will have lower boiling point. Since this is not branched, it will have higher boiling point. Simple. In which of the following forces, the London dispersion forces are not the only forces at play. Over here, bro, what is happening? Over here, bro, there's nothing. London dispersion. Over here, non-polar, covalent. So, I mean, it has London dispersion, London inside. This, oh, this does have London because everything has London in the world, but it also has an N and an H. So that means hydrogen bonds. So boom, lock in the answer C. Over here, London and hydrogen. AlCl3, London is there, nothing else. Covalent bonds are working. Over here, same thing. But over here, we have hydrogen bonds. Boom. Okay. Okay. Wait, no. Shit, I messed up. So we're looking for the molecule with only London forces. So that's that. I just told the answer at the start. Okay, I just simply okay. This, as I said, boiling point is inversely directly proportional to molar mass. So C6H6 will has a higher mass, so it has a higher boiling point. That's nothing. Explain the connection between intermolecular forces and phase changes. Okay, see, liquid O2, London forces. Okay, in between, because O2 is non-polar and non-polar covalent. So the forces which will act between them is London. So O2 and O2 and O2 and O2, the forces between them will be London dispersion forces. Because they're not polar, so they won't have a charge to attract to any base. So this is not mercury metallic bonds. Any means like any metal you see, metallic bonds. Huh? Okay. CH3I, we have an CH3 and I. We can understand that this has a dipole because I is more electronegative than H. Very simple concept. So dipole, dipole. Over here we have an OH. Straight away you see OH. If you see OH, NH, FH, don't even think about it. Straight hydrogen bonds. Moving on next. Explain the intermolecular forces. Wait, this is the Henry's law, so I'm going to explain Henry's law. Question before this: predict which substance has a lower vapor pressure. Vapor pressure means like it gets evaporated less. To get evaporated, you need to have a low boiling point. To have a low boiling point, you need to have a low boiling point. You need to have weak forces. So we just are looking for the weak forces. Over here, you can see we have OH. So hydrogen forces, the strongest force there is. But over here you can see there's 3 points of attachment. So hell yeah, this is going to be stronger. Water, H2O, this has H and O, H, H, OH, hydrogen bonds, definitely stronger than this shit. Okay, this stuff, this we need to understand. This is the phase diagrams for CO2 and water. Let's explain H2O first. So this is basically a temperature pressure graph. Temperature goes here, pressure goes here. Okay. This is solid, this is liquid, and this is gas. The point at which all three meet, it's called the triple point. Okay. I'm just explaining the graph here. Very simple concept. So, very important point to note here is the atmospheric pressure. 1 atm is the pressure that we all live in, that we all are adapted to, that we can survive in. So over here, a very crucial thing to note is that 1 atm is above the triple point. What does this mean? This means that in atmospheric pressure, normal pressure, okay, we can obtain all three phases of water just by increasing the temperature. What do I mean by this? Let's take a pan. Let's heat that shit up. Don't close the lid because that's going to change the pressure. Keep the lid open, okay? You place an ice cube here now. Solid. After some time increasing temperature, it becomes liquid. Correct? After some time increasing the temperature more, it becomes a gas. But the pressure around it has remained the same the whole time. That's important. Because of the triple point being lower than atmospheric pressure, at the atmospheric pressure we can obtain all three states: solid, liquid, and gas. Okay. Now we need to look at this point here: supercritical fluid. At one point over here, like that, okay, extends from here to there, like that. There comes a point called supercritical fluid. It is a state between liquid and gas. It has the properties of gas, it has the properties of liquid. Example, liquid nitrogen. Have you seen those crazy things like liquid nitrogen? They serve ice cream with it. They just pour liquid nitrogen and it's like a liquid, but it's gas also. You get me? That's supercritical fluid. That's an example. Okay, so that is anything above this temperature, anything above the critical point. The critical point being 374 degrees. And the questions are very simple over here, guys. Look at this. What is the state of water at 0.009 degrees Celsius and 6.3? Just look at the 6.3 atm is given over here, and then get the temperature. Temperature is 0. Okay, where is that? Right here. That is the triple point. What is the state of water? It exists in all states. Boom. Normal melting point and normal boiling point. What does a normal mean? Why not just melting point, boiling point? Normal melting point means the melting point at 1 atm. Okay? And normal boiling point means the melting point at the boiling point at 1 atm. Simple? Simple. What is state of water at minus 20 degrees? Just this is very simple, guys. Just look at it and you can find out. CO2. Okay? What we need to notice the differences here. Difference is, okay, the solid liquid boundary here has a negative slope. Means that it's leaning this side. What does this Why do we need to know this? Why is it important? It just tells us that the density of liquid water is more than the density of solid water, means ice. Because if we take a point here and we increase the pressure, we move into liquid. What do I mean by this? High density, to understand which medium is higher density, we need to look at which medium exists in higher pressure. Simple. Okay? So if I take a point anywhere here, anywhere, I take a point anywhere in the graph. If I take a point here, go up in pressure, it's going to come in liquid. If I take a point here, go up, over here it may seem like it's going to go in solid, but you see this is slant. So slowly over time, it gets like tilted over time. So if you go up, see, it's still going to go into liquid. So basically saying that liquid exists at a higher pressure. And if what the medium that pressure exists at a higher pressure has more density. Now, but over here we see it has a positive slope. What does this mean? That solid state of CO2 is more dense than liquid. Anywhere you take this, if you take this, it's gonna slope and form. It's gonna form a slope. I mean, not now, but later on. You keep extending, it's gonna form a slope. It will be visible. Taken any point at any point here, you go up. It's going to be, you increase the pressure. It's going to be at solid. That means that solid CO2 at higher pressures exists in solid state, which means that solid is more denser. Same questions, very simple, guys, very simple. All the points over here are same, but look over here. Triple point here, 1 atm here. 1 atm is lower than the triple point. What does this mean then? What does it change then? All we can notice over here is that at 1 atm, the states that we can obtain by increasing the temperature is only solid and gas. We cannot obtain liquid CO2 in atmospheric pressure. We need to increase the pressure more than the normal atmospheric pressure to obtain liquid CO2. Simple, guys. They're gonna ask very simple. It's gonna be MCQs anyway, so relax. You can just look at these questions. Super simple questions, guys. Easy. Explain the effects of intermolecular forces. Okay, very simple over here. See, guys. Okay, strong intermolecular interaction between solid and solvent are the more likely the solute. Like dissolves like. Polar solvents dissolve polar solutes. Non-polar solvents dissolve non-polar solutes. Very simple over here. Basically, it's trying to say if this is the solvent and this is the solute, if they both can form hydrogen bond, then definitely they will be soluble. That's all they're trying to say. If these guys are not a match, they're not gonna mix. That's how life is. If you and your bitch don't match, you're not gonna mix. Okay? So if you want someone to come inside you, whoa, that's outrageous. Shouldn't say that. Okay, scratch that. If you want someone to, no, let's not even take those analogy anymore. Okay, if you want to mix solvent and solute, you want them to be able to form bonds with each other. Simple as that. What factor determines solubility? Polar dissolves stronger and like dissolves like. Non-polar substance dissolve polar. Non-polar substance dissolve non-polar. Temperature and gas. Of course, when you add something in a hot water and mix it, it's going to dissolve faster. Simple. If you pressure means like it can be anything. You close it and you shake, you mix. That's pressure. Increases solubility. Think with your brain. It's very simple. One point you have to remember is polar dissolve polar, non-polar dissolve polar, non-polar. Other than that, it's just like what temperature and pressure. You don't know that. You're 20, 18, 19 years old. You should know that. Then after this, guys, it's just formulas. It's just formulas. Henry's law is solubility. The way how you find out the solubility. What is the solubility of sugar in water? It's going to be very high because it dissolves very easily. How to find that? You'll be given a Henry's constant of, this is different for every solute or solvent, and then this pressure. That's it. The questions will be very simple, guys. Obviously, at 298 K atmospheric pressure, that means 1 atm. It was determined that this many moles of CO2 was dissolved in this many liters of water. The Henry's law constancy they're gonna give you is 30. Determine the percentage of CO2 in the atmosphere. You can see the calculations over here. It's all math. I don't want to do the math, okay? Because the next lecture by methane is going to be filled with maths as well. But they're very simple. Once you know the formulas, very simple. Okay, we all know basic maths. They're just gonna give us they're gonna tell us to learn a formula, and then as questions, because it's MCQs, guys. They're not gonna give us fat as shit questions. Okay, they're gonna give us questions which we can easily solve on a calculator. Understand? So they're gonna give us all the values that we need, and we just need to plug it in the formula and then get the answer. Compare the solubility of glucose, cyclohexane in water. Glucose is C6H12O6. H12O6. H and O, so it forms hydrogen bonds with water. Very simple. And glucose is polar, so it dissolves in water quickly because water is polar as well. Polar dissolve polar. Cyclohexane isn't polar, so it won't dissolve in water because non-polar does not dissolve in polar. Simple, guys. Simple, 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 simple. Vitamin A and C, you see OH is here, but it has only one point of attachment. Over here, it has more points of attachment, so hence this will dissolve more. Simple. Solvation, hydration. What happens when you dissolve water, sugar, salt, and water? NaCl, table salt. You dissolve it in water. What happens? Why does it dissolve like that? NaCl splits into Na plus and Cl minus. Okay. And water molecules, let's draw them like this. This is O and this is H. We know that oxygen being more electronegative, it will have a negative charge and these will have positive. Okay? So, NaCl, Na plus, Cl minus, they split. Now, around the Cl molecule, Cl minus ion, what happens is water, this is what happens, see, Cl minus, why is it so fat? Cl minus, around this, the water molecules arrange themselves like this. This being the O, and these balls being the H. So this has minus, 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 minus. These have plus, 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 plus. You see how they're attracted over here? That's what happens. The process of the water forming this hydration shield around the solute to dissolve it in is called hydration or solvation. Understood? Simple, right? Same happens for Na plus, but the water molecules, water molecules flip like that. Okay? Simple, right? Simple, 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 simple. Not gonna ask a lot of questions on this anyways. Then this look at this table, guys, over here. This table right here. Take a screenshot of this. All the formulas that you need to learn. Learn these formulas. Very simple. I'm just gonna tell you this. I'm just gonna explain this thing over here very fast, very quick. Yeah, when you are asked to find the number of moles, when they say moles of B, how do you find the moles of me? Over here, you divide the given mass by molar mass. Okay, what I mean by this? Let me see. Like say over here they're given us 120 grams of NaOH. So given mass is 120. And the molar mass of NaOH, 40. Once I get the answer to this, that's the number of moles of NaOH. Simple? Simple enough? That I just wanted to explain that. Very simple, guys. The numericals over here are very simple. The harder numericals are in the next slide, next lecture, done by Mateen. Okay, that's going to be a bit more harder than these. These just learn the formulas. It's plug and solve. Okay, they're going to give you the values. Just do those things. It's going to be very easy. We have homework. This just guys, it's very easy. Please listen to me. It's very easy. Dilution concept. Let me explain it to you. You take a concentrated solution. That means Number of solute is more than solvent. Okay, solute more than solvent or in high quantity. Okay, you add solvent into it, it becomes a dilute solution. What do I mean? Basically means the solvent particles, the amount of solvent, no, the amount of solute particles remains the same. Solvent increases. Basically, I take water, glass of water, add 1 tablespoon of salt, mix that bitch in. Okay, it's a fairly concentrated solution. Okay, fairly concentrated. I add more water into, I pour this water in a huge jug. It's in a huge jug now. Did I increase the number of salt molecules that I put inside? No, I didn't. But what did I increase? Increase the number of water molecules. So now that's a dilute solution. Khalas! This is the formula for it. Molecule, the molarity and volume. Volume they'll be given. Molarity, you just learn the formula that over here that I have for you. Osmosis also one very easy. Here's the formula. This formula. This is initial and final. Initial and final. Learn these. What's I over here? I is the dissociation constant. Basically NaCl. Take NaCl. After splitting it forms Na plus Cl minus. That's 2. So I will be 2. What else can you take? Give me an example. Let's say 2 NaCl. Okay. 2 NaCl will split into what? 2 Na plus 2 Cl. Okay. That's 4. Okay. Colloids, we're getting closer to the end. I'm so happy. Okay. I know guys, I skipped a lot of the formulas, but I did that because it's easy. Okay. I did this stuff in high school. Indian syllabus taught me this. So it's very simple, guys. In Indian syllabus, you get much more harder than this. But for now, I'm just telling you, it's very easy. Learn the formulas, plug in, you solve the homework questions, go over these questions. And once you go over these questions, it's going to be very easy. Okay. And if you don't feel motivated enough to learn this, just remember that there's a 15-year-old Indian sitting in India, okay, who knows this and who can do this course better than you. That should give you motivation. Majority of the 15-16-year-old Indians can do this course, but you can't, and you're tired, and you're continue. Colloids. Let's look at colloids. What is a colloid system? Okay, let me just explain this. It's very simple. Look at me. Homogeneous mixtures, heterogeneous mixtures. Okay, this water over here. Wait, let me just drink some. Water. I add salt in this and I mix it for some time. Can you look at salt water and tell that it's salt water? I mean, if you dissolve enough salt, then of course you can, but like you add 1 spoon, that's it. Mix it in. Can you tell that it's salt water? Can you? You can't. Okay, your eyes are not microscopes. So you can't tell. That is a homogeneous mixture. When the whole solution looks like one and you cannot differentiate it between solute and solvent. Also, I've been telling solute and solvent for a while now. If you don't know what that is, I mean, honestly, I don't feel bad because like I didn't explain. I'm very sorry. A solute is the part of the solution which is less quantity, and solvent is part of the solution which is more in quantity. Simple. Take glass of salt water. Salt is in less quantity. Wait, damn. Oh shit! I stopped recording. I'm gonna have to add the whole thing again. But it's cool. Add that in more quantity. Okay, that's solvent, then that's solute. Okay, water is in more quantity, so it's solvent. Salt is in less quantity, so it's solute. Now, heterogeneous mixtures. Take water, put a glass of mud in it. Glass of mud, just put a bit of mud in it. You think you can dissolve it enough to make it seem like it's clear? You cannot. At the end of the day, the mud particles are gonna fall beneath, they're gonna sediment in the bottom. Okay? And you can separate them, you can look and tell that that's a heterogeneous mixture. But what is a colloid? Colloid is somewhere in between. Okay, yani the molecules that the solute molecules in a homogeneous mixture, they're super small, so you can't see them, so you can't differentiate. But in a heterogeneous mixture, they're too big, so they fall down due to gravity. They get sedimented due to gravity. But colloids are somewhere in between. They're not big enough to get pulled down by gravity, but they're not small enough to be not differentiated. They're somewhere in between. That's what a colloid is. A colloid is made of two parts. Like any solution is made of solvent and solute, a colloid has its own terms. It's a whole different breed. Okay, what are these terms? I'm just gonna keep scribbling, because otherwise, if I don't, the screen's gonna turn off and then the video recording is gonna turn off. So yeah, colloids. They have two over here. You can see it's the dispersed phase and the continuous phase. Or I use this dispersed material and the dispersion medium. Let's take some examples over here. We have some examples here. Over here, see. Let's say aerosol. Let's take fog. Fog in the mornings. Yeah. What is that basically? See, if the molecules of water in the air were fat enough, they would fall down as rain. Okay? If they were small enough, you couldn't see. You would just be like, it's air. But in a fog, what happens is they're just big enough where they don't get attracted by gravity to the ground and cause rain, but they're not small enough to be not seen by the naked eye. That's what forms fog. Fog is a colloid. Okay? And over here, what is the dispersed material? Water is the dispersed material, which is dispersed along the air particles. And what is the dispersion medium? Air. Okay, let's look at some other examples and I can explain. Emulsion, milk. Basically milk and water, okay, that we're talking about over here. But let's look at, what else can we look at? Gelatin, cheese, all of this. These are all examples. Dispersion medium and dispersed medium, they're very common, they're common sense, you can explain, okay? Fog, mist, clouds are also colloids. Okay, clouds are basically like fog, but like joined together in one place. Okay, dispersed medium in that is also water, and dispersion medium is air. That's what a colloid is. Now, a colloid has certain properties. Okay, certain properties. What are the properties that it has? It has something. It does something called the Tyndall effect. Over here you can see Tyndall effect. What is a Tyndall effect? Over here, this is a colloid and this isn't. What do you see is different over here? You see this ray of light which you can see over here passing through here, but you can't see over here, but you can see here. Okay, why? Concerts, probably been to one. U Day, who all has been to U Day has seen that near the end of the night, they filled the whole stadium with fog. Why? Because fog is a colloid and it exhibits the Tyndall effect. And so when they pointed lasers through this fog, the light would scatter in the fog and it would look so cool. Yeah? So that is the Tyndall effect. If you point the lasers or these lights just normal air, you won't get that slight scattering effect. You won't get that cool effect. You won't get that concert vibe. That's the Tyndall effect. Okay? The ability of a colloid to scatter light because of the size of its particle and the beam light can be seen through the colloid. Okay? The particles are not very, very small, the point where it doesn't scatter at all. They're not very, very big where it's like on the ground, like mud water cannot scatter light, sorry. But colloids can. Okay? That's that. Types of colloid is basically, this continuous medium means dispersion medium, and these are all like types. I mean, what can they ask you on this? Not very lot to ask about this. Colloids can be stabilized. Okay, let's talk about hydrophilic and hydrophobic molecules. Hydro, water, means water. Philic, to love, okay. So many examples. Pedophile, whoa, that's the first thing that came into mind. Kid lover, under 18, okay. Philanthropy. Philanthropy. Tropy. Phil is the love of humankind. Boom. So over here, what it basically says is that this, you see over here, this is an example of a hydrophilic NH3, OC, COO. What is common in all of this? NOF is common. NOF. Remember NOF? So they all obviously dissolve in water because they have NOF. NOF can form hydrogen bonds. Water can form hydrogen bonds with NOF. Easy. Boom. Simple. That's a hydrophilic. Hydrophobic doesn't have that. It's non-polar. It doesn't have NOF. Finished. Okay? It basically repels water. Okay, you can see nowadays you get all that waterproof stuff. You add wax on your laces, you get waterproof laces. Basically, wax is non-polar. It won't dissolve in water. It won't interact with water. Finished. But now let's say, I want to dissolve a hydrophobic material in water. I want to. Okay, I just want to. What do you use to dissolve this? Okay, you can use something called amphipathic molecules. What are they? They're molecules structured in this way. Look at the way. A long hydrocarbon chain which is non-polar, okay, and hydrophobic. And then at the end there's a charged head which is polar. What happens is, see, this is micelle, okay? This is micellar. You guys, girls use micellar, okay? Girls, you use micellar. If you add usually some makeup particles, you add water, they won't mix and they won't get out. But you use micellar, they get out very fast. Why is that? Because micellar is an amphithetic molecule, and it's like this. It contains a long hydrophobic chain and one hydrophilic head. So what happens is, see, this is what happens. A micelle in water with oil drop. This is the oil droplet. So what happens is, these amphipathic molecules, they adjust themselves like this. They insert their non-polar heads inside, and they leave their polar heads outside. And since now the polar heads are outside, polar dissolves polar, so this whole molecule will dissolve in water. Yeah, I made the oil dissolve in water. That's what I wanted and I did it. Yeah, you just use a bit of chemistry. But when you use stuff like this, when you use aids like amphipathic molecules, it's not called solubility or dissolution anymore. It's called emulsion. Okay? That's that. MCQs, choose the correct statement about the tetrachloromethane, bromomethane. The dipole moment of the compound increases in the given order. The polarizability of the compound increases in the given order. The type of chemical bond ionic. This one is correct, B, because the number of atoms, electrons are increasing, so the polarizability does increase. Okay. Choose the list of compounds shown below in the correct order of increasing boiling point. Boiling point is what? Boiling point is proportional to molar mass and inversely proportional to branching. Okay. Let's look at these two first of all. Automatically we can see this has more molar mass. Okay. Does this have more molar mass than this is the question? I think so, yes. So this will be the first thing, because it has the most molar mass, it's going to have the highest boiling point. Then I'm saying this because it has an O, and O can attach to an H in H2O. O can attach to an O, something like that. It's polar, basically, what I'm trying to say. So higher boiling point. And then we can come to this. Okay. But then there's another case also where we can say that this is a polar. Let's remove that. I'm going to remove this part. So yeah, guys, that was the lecture. It was big. I had a lot of concepts. I did go over the formula part, skim over it, because it's easy, guys. Trust me, you guys can do it. I believe in you guys. SCTs are going to be just MCQs. Trust, we can crack it. Come on, 57% for exemption. That's easy, man. Come on. I promise you guys, if you watch our lectures for before Medchem SCT, there's no way you're gonna not get above 57%. There's no way, because it's very easy, guys. 42 questions, you can't get above 25. You can't? Are you that stupid? We all can do it, okay? We all can do it. Imagine after saying all of this, I don't get 57. That's crazy. But we're gonna try. We're gonna try our best. We're gonna try to get exemption. And if you get exemption because of watching my videos or our videos, you gotta take us out for a meal. That's the deal. Take us out for a meal. That's all we're asking for. Okay. See you guys in the next lecture. The lecture after this is gonna be 3.2. I know this is just part 1. That's crazy to even think of. This is just part 1 of the third lecture. Second part is going to be done by Metin, and then we're going to do the 4th lecture, 5th lecture, get over with Medchem before the SCTs. Don't worry about that. See you guys later. Bye.